So today we're actually going to start the last, technically, two sections in chapter 5. However, we're going to kind of look at them together just because to me it makes more sense and they go together really, really well. And they flow better when we look at kind of the entire picture versus like breaking them apart, kind of like your book does. So the first thing we're going to start with is by looking at a couple of definitions. Now, we've used all of these words before, but we're just going to kind of write them out to make sure we can kind of recall the differences. So remember that a root is going to be the solution. To the equation P of x, which this is your polynomial, so P of x equals 0. Your zeros are going to be any x value that makes y equal 0. And then lastly, your intercepts are going to be ordered pairs of the points where the graph intersects the x-axis. And if we think about it, remember that if we're on our x-axis, then your y value would have to be 0, which means that your intercepts are also going to be the same values as your zeros. And then likewise, remember that y, another way that we can write y is f of x or p of x. And so your zeros are also going to be your roots. So all of these things are slightly different. However, we're going to basically set our equation equal to 0 and solve for our x's to find any of these. So the process is basically the same, and we can kind of think about them meaning the same thing. All right, next we have what's called the fundamental theorem of algebra. And especially because it says the fundamental theorem, it sounds like it's probably pretty important. And it is. It's something that gets used a lot, and it's something that you'll continue to use, even if maybe not by like its name, but it's just like this idea that comes up in basically any other math that you do. Okay, and so basically what it says is every polynomial of degree n has n number of roots. Now, something kind of like a asterisk or another part that we kind of have to keep in mind is that this includes repeated and complex roots. So before we kind of had a theorem that told us that the degree, we know that a function has to have the degree or less real number roots or solutions. And now this one's telling us that it has to have exactly the same number of roots. However, it gives us the kind of exception that this includes any repeated or complex roots. And so we know that say we have a degree of 3 and we only have one real root, that tells us that we're then going to have 2 complex roots because your degree has to equal the number of roots you have. So let's look at an example. This tells us to solve each equation, state the number and type of roots. So we're going to solve on that first one. Hopefully we notice that it is a quadratic. So we would want to factor it if we can. If we can't factor it, then we'll use our quadratic formula. So it says I have x squared plus 6x plus 9 equals 0. Again, I'm going to use my AC method. You're welcome to use whatever method you feel most comfortable with. So I'm looking at what 2 numbers multiply together to give us 9, that add together to give us 6. In this case, it's going to be the same number. So I'm going to get x plus 3 times x plus 3. Now remember that because my leading coefficient is 1, I'm allowed to just jump to that step. I can say, okay, my 2 numbers are 3 and 3. I'm not going to break apart that middle term just because my leading coefficient is 1. I know that those are going to be my 2 factors. Now, if you feel more comfortable breaking it apart and factoring by grouping, that's fine. Whatever works best for you. So then remember, once we have it factored, we're going to set our factors equal to 0. Now, in this case, because they are the same factor, we're going to get the same solution or the same answer. So really, our answer is just going to be x equals -3. But now let's think about this. We said that our degree has to equal our number of roots. Well, our degree is 2, because it's my biggest exponent, but I only have one answer. And this is where that little asterisk dot at the bottom comes into play, is because we said that it has to have the same number, including repeated roots. So I have an answer of x equals -3, but it is repeated or has a multiplicity, okay? So multiplicity is just a fancy word, basically for multiple. So this is repeated, and you might see, in your book, it might say has a multiplicity, but just realize that that means the same thing. And I don't care which one you use. Just realize that they do mean the same thing. So EU has a multiplicity of 2, or we can think of it being repeated twice. So if we include that repeat, we do indeed have 2 answers. So we would say, so it asks us to state the number. So we have 2, and they're both integers, which is the type of root. You could say 2 real integers, but we want to try and get as specific as possible. So I would say 2 integers. So let's look at our next one. I have x cubed plus 25x equals 0. So we are going to try and factor it first. Remember that our first goal is to always try and factor out a greatest common factor if possible. In this case, both of my terms have an x, so I can factor that out. Now notice in my second parentheses, I have a quadratic expression, and there's only two terms. So we're not going to be able to use our AC method. Remember that for our two-term quadratics, we do have a equation or a formula. It is our difference of squares. And notice that 25 is a perfect square. However, the problem is that it is a sum of squares, and we don't have a formula for that. So we're going to go ahead and just set each of our factors equal to 0 from here. And for our first one, it's kind of already solved for us. We just have x equals 0. That's my answer. Now for our second one, we do need to do a little bit of work. Again, we're trying to get x by itself. So I'm going to subtract that 25, and then I'm going to take the square root. Be careful though, because remember when we take the square root, we have to add a plus or a minus. And that's going to be important here in just a second. Now, because we have a negative underneath our radical, we should recall that that is going to bring out an I. So we would have plus or minus I square roots of 25. So my I takes care of the negative. And then we should know that the square root of 25 is just going to be 5. So we get plus or minus 5i. Now notice that our beginning or our starting equation had a degree of 3, which means that I need 3 solutions, including our imaginary or complex solutions. So I have x equals 0. So I have 1 integer root. Okay. And then notice that if we had forgotten that plus or minus, we would have only had 1 complex root, which would have only added up to 2. So we would have known that we were forgetting something. So that's why we should remember whenever we start counting, oh, I only have 2, I'm missing 1, I go back, I look at, and I see I forgot my plus or my minus. So then I know that I have 2 complex. You could also put imaginary here, that would be fine, but we have 2 complex roots. All right, next up we have what's called the rational zero theorem. And basically this is just another tool that helps us to kind of decide which zeros are going to be possible for any polynomial. So when we start looking at solving polynomials, this is going to be really important because sometimes when we can't factor and we can't use one of our factoring formulas, we're going to need to start using synthetic division. And we'll go over that here in a little bit. However, we want to be able to have a list to pick from. We don't want to just have to pick any number and go from there. We want a specific list of numbers. And then we will know, okay, I don't know which one of these works, but I know that it has to be one of these numbers. And that at least gives us a starting spot. And this theorem gives us that starting spot. So let's say if P of x is a polynomial then all roots of P of x. So again, remember roots, solutions, zeros, they all kind of mean the same thing. Must be of the form plus or minus P divided by Q. So they have to be a rational number, okay, where P is a factor of the constant and Q is a factor of the leading coefficient. So basically, we're going to be looking at the constant and the leading coefficient and creating a bunch of options, bunch of fractions that can be our zeros. So let's go ahead. I just want to give you a quick little example. So let's say I had 4x to the third plus 3x squared plus 9 x minus 16. So remember, I want to look at two things. I want to look at my leading coefficient, and I want to look at my constant term. So remember that my p values are going to be my factors of my constant term. So let's look at our factors of 16. So I'm going to have a 1. It's going to be a factor always. And I know that 2 also goes into 16. 3 does not. Then I have 4. Well, 4 times 4 is 16. And then I notice that 2 times 8 would have to give me 16, and 1 times 16 would have to give me 16. Then remember, we also need our factors of our first one. So that's going to be my Q values. So again, I'm going to have 1, 2, and 4 this time. So then basically, to create that list, I have plus or minus P divided by Q. This is going to be a list of all of the possible zeros. Now, remember that this isn't a list of the actual zeros. You still have to test these and see if they work. But I know that this is a list of all of the possible zeros. And basically, I'm just looking at all of the different combinations that I could make. I'm going to start with my first Q value is 1. And then I'm going to look at my first Q value. Well, 1 divided by 1 gives us 1. Then I want to stick with that first P value, but I want to go to my next Q value. So I would have 1 divided by 2. Continuing on, I would have 1 divided by 4. And I move on to my next P value, which is 2. So I do 2 divided by 1 is 2. Well, then notice that if I were to go to my next one, I would have 2 divided by 2. Well, 2 divided by 2 gives me 1, and I already have that on my list, so I'm not going to write it again. And then I have 2 divided by 4, which would give me 1/2. Again, I already have that on my list. I don't need to list it again. So then next we move on to 4. So I have 4 divided by 1 gives me 4. 4 divided by 2 gives me 2. It's already on my list. And then 4 divided by 4 gives me 1. And it's already on my list. Next up, we have 8. Then we have 8 divided by 2 gives us 4. And 8 divided by 4 gives us 2. And both of those are already listed, so we're okay. Then I have lastly 16 16 divided by 1 is 16, 16 divided by 2 is 8, and 16 divided by 4 is 4. The only one that's not on my list is 16. So then, just from here, I would want to say, okay, so remember, it can be the positives or the negatives of all of these, and then I'm just going to list them in numerical order. And those would be all of my options for a rational zero. And then, like I said, we're going to have to use synthetic division to test those out. Now, this one says to find all of the zeros of this function. So we want to start by just listing out again what are our options. So again, we need P and Q. So notice that my P values are going to be factors of 80, and my Q values are just going to be factors of 1. Well, what's nice about that is because my Q is just 1, all of my options are just going to end up being those factors of 80, okay? So again, we always want to start with our smallest, so 1 goes into 80. Then 2 also goes into 80. 3 will not, but 4 will. Five also will, and then 8 will. Then looking at 9 will not, 10 will, and notice that this is kind of where we start getting into our multiples. So notice that like 10 times 8 gives me 80. So then our next one, we would want to say, okay, what times 5 gives us 80? That's going to be 16. Then we're going to have 20, 40, and 80. Okay. Now realize that this is the plus or the minus of all of these. And like I said, remember from when we tested in our previous notes to figure out if something was a factor or not, we're looking for a remainder of 0. So this is my list of options. Now I need to test them using synthetic division. So I'm going to try 1 first. And then I'm going to write my things, my coefficients for my polynomial. So I'm going to have 1. Notice that I'm missing a third term. So it's going to be 0, then negative 18, 12, and 80. So my first step is to bring down my 1. 1 times 1 gives us 1. 0 plus 1 gives us 1. 1 times 1 gives us 1. Negative 18 plus 1 gives us negative 17. 1 times negative 17 is negative 17. Negative 17 plus 12 gives us negative 5. Negative 5 times 1 gives us negative 5. And so we get 75. Well, notice that 75 is definitely not 0. You can go back and double check your work, make sure you didn't mess up anywhere. But that tells me that 1 is not going to be one of my factors, is not going to be one of my zeros. Okay? And then we would continue down that road. However, hopefully we notice that for something like 80, there are a lot of options. So it would be nice if we had a way that would maybe narrow that down even more. So what we want to do now is look at a graph, because this is going to help me narrow it down a little bit. Now, remember that when I'm looking at a graph, I'm only going to be able to see the real zeros. And so that's why I said this narrows it down, but it doesn't necessarily give me all of them. So I'm wanting to look at the graph of y equals x to the 4th minus 18x squared plus 12x plus 80. And we should get a graph that looks like this. Again, I would use a graphing utility, calculator, something like that, because it's not going to be very fun to try and graph this by hand. So notice that I have two zeros that I can see right off the bat. We do have a fourth degree polynomial, so we know that we're still missing two other zeros, but at least this gives us a starting spot now to know which ones that I should maybe try next. So I'm just going to go ahead and start with -2. That helps me. So I'm going to do -2. And since from our graph we saw that it indeed is a 0, we know that we should get a remainder of 0. So we're going to go through our synthetic division. I bring down my 1. -2 times 1 is -2, plus 0 is -2. -2 times -2 is 4, plus -18 gives us -14. Times -2 is going to give us a positive 28. 28 plus 12 is going to give us 40, and then 40 times -2 gives us -80, which gives us 0, which is what we should get, because we said it is a 0, so I should get a 0 as my remainder. So we're still missing a couple of our zeros. So from here, we need to factor it further. But just like when we had the directions that said to factor completely after we found a 0, we don't want to go back to the beginning, okay? Because notice that if I were to do this again with -4 and I started with my first one, well, that would show me that both of those are zeros, but it doesn't help me factor it further in the end. So what we want to do now is take our quotient from our first 0, and we're going to convert that back to an algebraic expression. So remember that it goes for our we have remainder. So we have remainder is 0. Then this is going to be our constant, x squared, and then x to the third. So those are going to be my coefficients that I'm working with. So I would have x to the third minus 2x squared minus 14x plus 40. So basically, we're starting this process over, but now we're using this polynomial. But the nice thing is that it's actually going to help us reduce our list a little bit, because now not only does it have to be a factor of 80, it also has to be a factor of 40. So that's going to help me out a little bit, because 1 will still work, 2 will still work, 4 and 5 will still work, 8 and 10 and 20 will still work. But notice, and then 40 will still work. But notice that my 16 and my 80 don't work any longer. Okay? So next up, we're basically going to start this process over again. We would look at, okay, I'm going to look at my list, but be careful. I've already tried 1. I know that 1 doesn't work for my original function. That means it's also not going to work for my new function. So I don't need to test it again. I would continue down my list. Lucky for us, our graph gave us another option. So remember that option was -4. So I'm going to go ahead and use that one. But when I set up my division, I want to use my new function now instead. So I'm looking at 1, -2, -14, and 40. And then I just start the process all over again. I bring down my 1. 1 times -4 is -4. -4 plus -2 is -6. -6 times -4 is a positive 24. 24 plus negative 14 gives us a positive 10 times negative 4 gives us negative 40. And so we do indeed get a 0 as our remainder, which is what it should be because we know from our graph that negative 4 worked. So then from there, so far I have found 2 of my solutions. I know that negative 2 works. I know that negative 4 works. I don't have any other options from my graph. So this is where I said using our quotient is going to be helpful. Because now notice that again, if I were to convert this quotient that I have here to an algebraic expression, I would have x squared minus 6x plus 10. And because we've broken it down first to a third degree, now to a second degree, we know how to factor or solve a quadratic without having to do more synthetic division. So if I wanted to look at factoring this, I would say, okay, what multiplies together to give me 10 that adds together to give me negative 6? Well, let's see. I have 1, 10. Those aren't going to give me negative 6. 2 and 5. Those aren't going to give me negative 6. I don't have anything. So remember that if I don't have any numbers that multiply together to give me that last number, that add together to give me my middle number, it's not going to factor. So we need to use a different method. So you could either use completing the square, or we could use our quadratic formula. Either one's going to work. I'm going to go ahead and use our quadratic formula, but like I said, either one will work. So I have x equals negative b, which is going to be, let's just write out our formula first. Sorry. So x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So notice my a is 1, my b is negative 6, and my c is 10. So I'm just going to plug those values in. Well, a negative 6 is just going to be 6 plus or minus. Negative 6 squared is going to give us 36. And then we have 4 times 1 times 10, all divided by 2 times 1. So 4 times 1 times 10 is going to give us 40. And so notice that I have 6 plus or minus the square root of negative 4. And hopefully we recall that if I have a negative underneath my radical, that means that I'm going to get an imaginary number. So the square root of my negative is going to give me my I, and the square root of 4 is going to give me that 2. So I have 6 plus or minus 2i divided by 2. And then hopefully we notice that 2 goes into both my 6 3 times and the 2 1 time. So we're left with 3 plus or minus 2i. So we get 2 imaginary solutions because 3 plus I would be one solution, and then 3 minus I would be our second solution. So notice that we have 2 real integer solutions, and then we have 2 imaginary solutions, which is why I said that we can use our graph to help us eliminate some and to find a good starting spot. But some of the time, the graph isn't going to be enough. We're going to need to use some of those other skills and equations and formulas that we've used and learned as well. Thinking back to our fundamental theorem of algebra, I have a degree of 4, which means that I need 4 zeros. Well, I have 2 real zeros, 2 imaginary zeros, so that is 4 zeros. So I know that I've found them all, which is a nice thing to know because then I don't have to keep looking or keep testing or anything like that. All right, let's try one last example all together just to make sure that we have kind of this down. So I have 5x to the 4th minus 8x cubed plus 41x squared minus 72x minus 36. So again, I want to look at my p's divided by my q's. So notice that our p's this time are going to have to be factors of 36. So my options for that would be 1 and 2 and 3 and 4, not 5, but 6 and 9 and 12 and 28 and 36. And then notice that our q's would be the factors of my leading coefficient, which is going to be 1 and 5. So notice here that if I looked at my combinations of p divided by q, I would first want to start with 1 divided by 1 is 1. Then we get 1/5. Then we would have 2 and 2/5. 3 and 3/5. 4 and 4/5. 6 and 6/5. 9 and 9/5. 12 and 12/5. 28 and 28/5. And then lastly, 36 and 36/5. Which is a lot of options. Again, so again, I'm going to go back to, okay, what can I do to help me eliminate some of those? I can look at my graph. So let's go ahead and do that. So we have 5x to the 4th.
Good morning, teachers and students. Please stand for the Pledge of Allegiance.
Minus 8x to the 3rd plus 41x squared minus 72x minus 36. So again, looking at my graph, I notice that I have negative 0.4 and 2. Hopefully, we can kind of go through some of our fractions here in a second, and we can figure out which fraction is the negative 0.4. But at least it gives us a good starting spot of 2. So that's where I'm going to start. I'm going to do my synthetic division. So I have a 2 on the outside. Then I have 5, negative 8, 41, negative 72, and negative 36. And remember, I'm looking for a remainder of 0 in order for this to work. And so we do indeed get a remainder of 0. Now again, remember that if we were to convert this back to an algebraic expression, we would have constant x squared x to the 3rd. So we would have 5x to the 3rd plus 2x squared plus 45x plus 18. And now we know know that our second one is going to have to be a fraction. So hopefully we recall that 1/5 is going to be 0.2, which means that 2/5 would be 0.4. And we know that it's negative. So our next one, or our next synthetic division, we want to use negative 2/5. We have a fraction, that's okay. We should still end up with a remainder of 0. But this time, remember, I want to use my new polynomial, not my original one. And then I start my process over again. I bring down my 5. Negative 2/5 times 5. My 5s are going to go away. And so I would just be left with a negative 2. If I bring that down, I'm going to get 0. So then 0 times anything gives us 0. Then I get 45. Well, now notice that if I have, I'll show you over here on the side. If I had negative 2/5 times 45, notice that 5 goes into 45 9 times. And then I would have a negative 18. Because negative 2 times 9 would give us 18. So now when we add down, we do indeed get 0. So then remember that we have 2 of our zeros so far, negative 2/5 and 2. And then to find our last 2 zeros, because they weren't quite clear from our graph, I want to look at this new polynomial from my quotient. So I would have 5x squared plus 45. And we're wanting to solve that equation. So notice, hopefully, that we do indeed have a common factor of 5. So we could factor out of 5 first. And we would be left with x squared plus 9 equals 0. Now, notice that because I have an addition sign there, we can't use our difference of squares because it's a quadratic. So if I divide everything by 5, 0 divided by 5 just gives me 0. So now we can just go ahead and solve this. So I want to go ahead and subtract my 9 and then take the square root. So notice that when I take the square root of a negative 9, again, I have a negative underneath my radical, so that's going to give me an I. And then the square root of 9 just gives me the 3. So I have 2 as a 0, negative 2/5 as a 0, and then I have 3i as a 0. But wait, that's only 3 zeros. My fundamental theorem of algebra tells me that I should have 4 zeros. So I'm missing a 0. Oh yeah, I forgot to put my plus or minus in front of my square root. So not only do I have a positive 3i, I have a negative 3i as well, and that gives me my 4th 0. And that's actually a rule or theorem as well, is anytime that you have a 1 imaginary or complex 0, you actually have to have the opposite of it as well. So they're always going to come in pairs. Now, some of these problems are a little long, but none of the steps are necessarily hard, and they can just get a little long. So make sure that as we're working through these, that we take our time and just do each step as they come up.